All right, this is the stoichiometry unit 8 notes for the session. I'm going to do them in 3 parts because that's really kind of what we talked about, and what the homework is it's broken into 3 parts. So you will need a calculator, you'll need a pencil, and you'll need paper. Okay, part 1 is really just the arithmetic of equations, and it's stoichiometry. So the calculation of quantities in chemical reactions, that's the definition of stoichiometry. So a chemical equation, remember, starts with reactants and ends up with products. So really it's just a way of finding amounts in chemistry, kind of like using the amounts in a recipe. So like if I have my apple cake recipe here, I would start out with like 5 apples and 2 eggs and 1 teaspoon of nutmeg and stuff, but all of that stuff comes together to one product. But if I don't use the correct proportions, then I might not get the correct product. So, interpreting chemical equations, the first thing you have to do is make sure that you always balance. That is the first thing you have to do, balance. What do we have to do? Balance. So, I have to put a 2 on both sides so that I can have 2 carbons and 2 carbons, but more importantly, I'm going to have 2 oxygens plus 2 oxygens on my reactant side, which makes 4 oxygens, and 2 times 2 on my product side makes 4 as well. So when I talk about representative particles, for my carbon monoxide, I've got 2 molecules. I've got 2 moles of those as well. Its mass, I could look up the GFM of carbon and also look up the GFM of oxygen. So I'd have 12.0 and 16.0, and I could add those together. Okay, and so those added together would be 12 and 16 is 18 grams. No, that's wrong. That's like 38 grams. My math's not well today. So 12 plus 16 is going to give me 28 grams, and 28 times 2, because I have 2 molecules of it, would give me 56 grams of it. That's why there's 56 grams there. Then remember to calculate that. We do it always to the 10th position, so that's 1 number after the decimal from your periodic table. Then for volume, we have 22.4 liters for every 1 molecule, but since we have, or for 1 mole, but since we have 2 moles, we take 22.4 and multiply it by 2, which would tell us 44.8 liters. And all of this is Unit 4 stuff, because we're talking about the conversions really with moles. And then for atoms, since we have 1 carbon and 1 oxygen, that's 2 atoms, and 2 atoms times 2 gives us 4. So here we have 1 molecule, we have 1 mole, we also would have 32 because 16 times 2 would be 32 grams. We have 22.4 liters, and we have 2 atoms. Then for this one, we have 2 molecules because the coefficient in front of it is a 2. We have 2 moles because, again, the coefficient in front of it's a 2. Then the mass, we would look up carbon, look up oxygen times 2, and then multiply all of it times 2. So that gives 88 grams, which means it's 44 grams just by itself. That's its GFM. And then we would have our 22.4 multiplied by 2 to get our 44.8 liters. And then we would have 6 atoms because there's 3 atoms in carbon dioxide times 2 is 6. So something to realize is the mass number and the number of atoms is always conserved. So these values always add up to the same number of products and reactants. They equal. But the moles, the volume, and the molecules may not always be conserved. Those values don't necessarily add up reactants and products wise. And the reason the mass and the number of atoms adds up is because of our law of conservation of mass. And that's why we balance chemical reactions, is because of the number of atoms have to be the same on the reactants and the product sides. All right, this mole map is something that you really ought to write down. You should use it on your test, but you could possibly be given moles of a certain substance, and you're going to want to convert them to moles of a wanted substance. And to do that, you're going to use coefficients from the balanced reaction, or the balanced equation. This is key, and this is really the only new part of this unit, okay? And this is what we call a mole-to-mole ratio, all right? So you put the moles of the given on the bottom, and you put the moles of the wanted on the top, because we're really just going to do dimensional analysis. So if we start with representative particles, we're going to have to get them from like atoms or formula units or molecules into moles. And the way to do that is going to be to divide by 6.02 times 10 to the 23rd. And if we start with mass, meaning we start in grams, then we're going to have to divide by the GFM to get to moles. And then if we start with volume, which means we start with liters or milliliters, then we're going to have to divide by 22.4 liters to get to a mole. So if you're given something other than a mole, you're going to have to convert to a mole first. And that again is back in unit 4. Then we'd create a mole-to-mole ratio, and we'll now be in moles of something else. If we want to find representative particles of the substance, then we're going to multiply by 6.02 times 10 to the 23rd. If we want to find mass, then we're going to multiply by the GFM of this new wanted material. Or if we want to find the volume, then we're going to multiply by 22.4 liters to get there. So remember, it's really about if you start in something other than moles, you have to convert to moles. Then you're going to do the mole-to-mole ratio, which is our new part. And then if you want something other than moles, you're going to have to convert to that. Okay? Really, all this is dimensional analysis. So mole-to-mole calculations, we can relate moles to reactants. Or the moles of the reactants to the moles of the products by creating what we call a mole-to-mole ratio. And we do that by using the coefficients from our balanced equation. These will be our conversion factors in our dimensional analysis. Okay? So, how many moles of aluminum are needed to form 2.3 moles of aluminum oxide? Well, the first thing, like I said, we're always going to start off with a reaction, and we're going to have a balanced reaction. So I am given 2.3 moles of aluminum oxide, but I want to find moles of aluminum. So I'm going to start with what I'm given, which is 2.3 moles of aluminum oxide. And what I'm going to do is now I'm going to create a mole-to-mole ratio. So I'm starting in the middle of my mole map. Again, I highly recommend that mole map be on your paper and you can access it at all times. If you're in class and you're listening to this, you might want to make sure you have it on your note card that you get to use. Okay, so we're going to put moles of Al2O3 on the bottom, and we're going to put moles of Al on the top, because we put the moles of what we're given on the bottom and the moles of what we want on the top. Then we will use the coefficients that are in front of those compounds as the number of moles. So we end up with 4 because of the coefficient of 4 in front of the aluminum right here on the top, and we end up with 2 because of the coefficient of 2 right here in front of Al2O3 on the bottom as the number of moles. Then that will allow us to cancel out the moles of Al2O3 on top and bottom, multiply by across the top, divide by everything on the bottom, and we end up with 4.6 moles of aluminum. Okay, we have 2 significant digits to begin with, so our answer only has 2 significant digits also. All right, my next one. How many moles of oxygen are required to react completely with 0.84 moles of aluminum? It's the same reaction. It's balanced. I'm being given my moles of aluminum, and I'm wanting to find moles of oxygen. So I start with what I'm given. Then my mole-to-mole ratio, I'm going to put moles of aluminum here on the bottom, and I want moles of oxygen on the top. And I'm going to use my coefficients. So I have 3 moles of O2 because that's a coefficient of a 3, and I have 4 moles of aluminum because that coefficient is a 4. Then I would multiply across, so 0.84 times 3 divided by 4. Okay, so when I do that, my mole ratio looks like this, and I would end up with 0.63 moles of oxygen. All right. So again, now we're going to have 17.2 moles of oxygen that's going to react with aluminum, and I want to find aluminum oxide. So I start with what I'm given, which is 17.2 moles of oxygen. I make my T chart, or my train tracks, or my T chart. I'm going to put moles of what I want on the bottom, and moles of what I want to find on the top. And then I'm going to use the coefficients in front of them. So 3 goes with this one, and 2 goes with this one. Multiply across the top and divide by the bottom. All right, so that would end up with 11.5 moles of aluminum oxide. Okay. When we're in the labs, and that really does finish our part 1, but when we're in the labs, we typically talk about grams and not moles. So what we're going to have to do is we're going to have to use the GFM to get from grams to moles, and then we can do our conversion factor, and then we can do our mole to mole ratio. Okay, I do have some examples of this, but I highly recommend that you go ahead and maybe do like worksheet 2 of your classwork, because worksheet 2 of the classwork is working on mole to mole ratios. It is actually taking it one step further and doing grams as well. But also I recommend working on part 1 of your homework, which is just the mole to mole ratios. So again, those answers are posted for the homework, as well as all the workout for the classwork is posted. So enjoy.